Hi. So far we know the following. We know if given an ODE y double prime plus p of x y prime plus q of x y equals 0, we know that if p and q are analytic at x equal x0, there exists two linearly independent solutions, okay, that are analytic at x equal x0, i.e. there exists two linearly independent power series solution to the ODE centered at x0. Now, if P and Q are analytic at x equal x0, we said that x0 is an ordinary point. Now, if either P of x or Q of x are not analytic at x equal x0, then we say x0 is a singular point. So we did this in the previous lecture, and we learned how to solve in the neighborhood of an ordinary point. In this lecture, we'll tell you a kind of singular points that are not in fact so bad, and that I know how to solve in a neighborhood of the singular point. So for this, let's start with an example. So if you have the ODE 2x squared y second minus 5x y prime plus 3y equal to 0, this, well, x is positive. This can be written as y double prime minus 5 over 2 over x y prime plus 3 over 2 over x squared y equal to 0. Now notice that this following equation is Cauchy-Euler equation. What is P of x? P of x is minus 5 over 2 over x. Q of x equals 3 over 2 over x squared. And we know that's Cauchy-Euler equation, and we know that x, P, and Q, in fact, are not analytic at x equals 0. So x equals 0 is a singular point. However, since Cauchy-Euler, I know that there exists a solution to the ODE of the form x power r with what? With r solving the quasi-linear equation, r solves the auxiliary equation 2r r minus 1 minus 5r, this is Cauchy-Euler, 5r, plus 3 equal to 0. Dividing by 2 equivalently can have r minus 1 minus 5 over 2r plus 3 over 2 equal to 0. But notice this minus 5 over 2 is nothing but x times P of x. And this 3 over 2 is nothing but x squared times Q of x. Okay, so keep this in mind. So if I want to factorize this equation, I get you get 2r. If you want to factorize this equation, you get 2r minus 1 times r minus 3 equal to 0. So you have a solution of the form x power half and solution of the form x power 3. Okay. Now, but the r solves which kind of equation? R minus 1. What is this minus 5 over 2? It's really x times P of x. because this is p of x. What is 3 over 2? It is x squared times q of x. So although x equals 0 is a singular point. So definition motivated by the following. Definition, given a second order ODE of the form y double prime plus p of x y prime plus q of x y equals 0. Remember, the coefficient of y second is always 1. We say that x equal x0 is a regular singular point if and only if two things. So it's a kind of singular point which I call regular singular point. So if and only if x0 is a singular point, i.e. either p or q are not analytic at x equal x0. And second thing is I should have x minus x0 times p of x and x minus x0 squared times q of x are analytic at x equal x0. So what is here in this case? What is x p of x? It's minus 5/2, which is an analytic function. And what about x squared q of x equals 3/2, which is analytic at x0? So in the following Cauchy-Euler equation, x equals 0 is a singular point, but it's not any singular point. It's a regular singular point. Okay. Now, if x0 is a singular point, if I call this 1 and call this 2, not satisfying 2, i.e. either, so it's enough for one of these two conditions not to be satisfied, either x minus x0 p of x or x minus x0 squared q of x are not analytic at x0. So it's a singular point and the second condition is not specified. We say that x0 is an irregular singular point. And there's no general method to solve in a neighborhood of an irregular singular point. This is a pretty bad point. It's a bad point. So in this lecture, we'll learn how to solve in a neighborhood of a good bad point. Okay, it's a regular singular point. It's a bad point. It's not an ordinary point, but let's say it's not that bad. I can still control it. Just a remark. Let's say I have y double prime plus p of x y prime plus q of x y equal to 0, where x0 is a regular singular point, i.e. x minus x0 p of x is analytic at x equal x0, which means I can write it as a power series centered at x0. This is what analytic means. Plus, 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 for absolute value of x minus x0 smaller than, I will call it RP. And also, x minus x0 squared q of x is equal q sub 0 plus q sub 1 x minus x0, because this is analytic, this new function now is an analytic function, plus q sub 2 x minus x0 squared plus, 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 for absolute value of x minus x0 smaller than RQ. Okay. Now what? Now x minus x0 is equal to this. Now this is approximately, for points that are very close to x0, this is approximately equal to, sorry, with that. This is approximately equal to p sub 0. What about this form? Because this is very close to 0, very close to 0. What about this one? This is approximately equal to q sub 0. So I have the ODE y double prime plus p of x y prime plus q of x y equal to 0. Now multiply by x minus x0 squared you will get this is x minus x0 square y second plus x minus x0 times x minus x0 times p of x y prime plus x minus x0 square q of x y equal to 0. Now the following ODE is approximately, this I will keep it, x0 square y second plus the following x minus x0 p of x is approximately p sub 0. So this is p sub 0 x minus x0 y prime plus x minus x0 square q of x approximately q sub 0 times y equal to 0. These two are not the same, but I'm saying I'm approximating the coefficient by this, but now this is a Cauchy-Euler equation with solution x minus x0 power r with r solving the auxiliary equation r times r minus 1 plus this is p sub 0 r plus q sub 0 equal to 0. Which means, and now I expect, so we expect solution to the original equation, which was this, to star. Notice, these are not solution x minus x0 power r, the solution to the approximated ODE. So I expect solution to star that are y1, which is approximately x minus x0 power r1, and y2 that is approximately x minus x0 power r2, where r1, r2 solve r minus 1 plus p sub 0 r plus q sub 0 equal to 0. Okay, this is what I'm expecting, and this is what I will build for in the following, in the couple lectures. For example, let me give you an example for this. If I have the ODE 2x squared minus x cubed minus 5y second minus 5x y prime plus 3 plus x y equal to 0. The following ODE, now 2x squared minus x cubed is approximately 2x squared y second for x close to 0, because the x cubed becomes much smaller than 2x squared. What about this one? This is minus 5x y prime plus, now this is approximately 3y equal to 0, when x very close to 0. Now we saw that the solution, the initial equation here is r minus 1. We solved this to r minus 1. We just did this here. Times r minus 3 equals 0. So the indices are r1 equal half, r2 equal 3. So we expect a solution y1 that is very close to x minus, well, x power half, and y2 is approximately x cubed. Now, in fact, and you will see later, we get solution of the form. The real solution for the following equation is y1 equal x power half times summation from n equals 0 to infinity of cn x power n, and y2 equal x cubed times summation from n equals 0 to infinity of dn xn. So the solution will be x power half, which is the solution to the approximated problem, times an analytic function, a power series, and x cubed, which is the second index, times an analytic function. And we still have to find, Cn and Dn. Okay. Now, this will not be always the case. Now, some cases will require terms involving x minus x0 log of x minus x0, which is also happen in the Cauchy-Euler equation. You have sometimes a log. Okay, so that's what that's motivating this chapter. We'll start with some few example about how to find singular points, and then we'll do an example, and then we will give the theory in general. Okay, about solving in a neighborhood of a regular singular point.